All right, so this is the next of our logarithms. Single logarithm, we're going to decompose into expressions of multiple logarithms. Now, we saw before, radicals don't play well with logarithms and exponentials. Since these are exponentials, we need to express this with an exponent. So the first thing I'm going to do is rewrite this as x times, this is now x squared plus 1 raised to the 1/2 power. Square root, we've now written this as exponential form 1/2 power. So remove any radicals at the very start, and now at least the exponents play well with the logarithms and the exponentials. Now we're at the same procedure as we were previously. We need to separate first and then move the coefficients down front. So first, separate this. So this is log base 5 of the first plus. So if you have the product is the sum of the logs. If we had division, then we would subtract the logs. So this is a log base 5 of x plus log base 5 of this expression raised to the 1/2 power. This is finished, but we have one more little piece of this bit. We may move this down to the front, and so we can write this as log base 5 of x plus 1/2 log base 5 of x squared plus 1. And so that is our result. We have decomposed this expression into multiple logs. There are no products, there are no quotients, and there are no exponents. All right, so now we'll take a look at one more of these, and then I'll set you to your task. Let's play, suppose we have log base 10 of, let's suppose we have x to the 4th over the 3rd root of y. All right, so same as before. First, let's get rid of this radical. 3rd root means 1/3 power. So we can write this as log base 10 of x to the 4th. Nothing happens there, but this becomes y raised to the 1/3 power. And then I think now it should be clear what happens with this. In fact, maybe you should start here and see if you can take this home see if you can work this by yourself. And so pause the video now. All right, so now let's see if we can, see if I can match your work, see if I can do this correctly. We have the logarithm of the quotient. Well, when you divide, this becomes the subtracting the logarithm. So we have log base 10 of x to the 4th minus log base 10 of x to the 1/3. And now the last piece in both of these is to move the exponents to the front. And so this is now 4 log base 10 of x minus 1/3 log base 10 of x. You actually could combine the, oh, I'm sorry, this should be a y. I'm sorry, this is a typo. This chalk is not working very well. This should actually be y to the 1/3 and y. So that's our final result with that little amendment there. And that's how we decompose these. So I think the rest of these you should be able to swing on your own. So after viewing these videos, this sequence of videos of applying the properties of logarithms, you should now be able to work on page 316. You should be able to handle items number 45 through number 69. At the very least, you should be able to do the odd numbered problems. That should give you enough to sort of practice this, so that using these properties becomes second nature to you, so that when you go into your physics class or your chemistry class or your calculus class, using these properties is not the issue you need to learn. You have bigger fish to fry in those classes. So learning these properties of logarithms, and this is the practice for that, that's an important piece of being able to handle these logarithms. One last little detail I want to mention is log base 10. And I'll just insert this here sort of as sort of as an appendix, as a sort of by the way, for several different reasons, logarithm base 10 has a special place in mathematics. It was so commonly used in probably, so we said the 1800s, so commonly used in the past that this is actually called the common log. The natural log is if we have base e. The common log is if we have log base 10. And this is so widely used that if you see logarithm without a subscript, unless you are explicitly told otherwise, this is presumed to be log base 10. Unless you are explicitly told otherwise, logarithm without a subscript is assumed to be 10. So this is similar to this. It's like this. If I have x to the third minus 4x plus square root of x plus log of x. There are in mathematics certain default settings, values that we assume unless we're led to believe otherwise. So we know these. If there is no coefficient, what do you assume? Well, it is assumed 1. You may, if you wish, write the 1, and sometimes it's helpful, but unless you're explicitly told otherwise, if there is no value here, we assume that's the default setting, this coefficient is 1. Similarly, if there is no exponent, we assume that exponent to be 1. Occasionally it's helpful to write that in, and if it is, then do that. But if you don't see an exponent, we assume it to be 1. Well, same thing here. Is this third root, fourth root? What root is this? The index, if you don't put an index, we assume that is the square root. So, coefficient, this is the default setting. This is the default setting for the exponent. This is the default setting for the index. Similarly, if there is no base written, that is assumed to be log base 10 unless you are explicitly told otherwise. In some standardized exams for graduate school and some other things, you're explicitly told otherwise. But in this case, generally, unless you're explicitly told otherwise, the logarithm without a base is log base 10. On your calculator, if you see log, that is log base 10, and that's what that computation represents. So, unless you're explicitly told otherwise, without a subscript, we assume that's log base 10. That's called the common log. Most of the work that you'll do in calculus revolves around the natural log, log base e. And so, again, that's just sort of an aside. And if you ever have reason to hit log on your calculator, you're doing logarithm base 10.